All right, so then I'm going to grab the data to have it next to me. Right there.
So all of our lines are going to be a little different.
Yes, they're all going to be a little different. So I'm just going to show you a couple of procedures to go about how to find your line. All right, so let's see. I picked what? 1950? No, let's see. 1952. That look right? 23.7. Yeah, so there's one of my points. So that's my upper point right here. And then the other point, this one right here is 1984. Would be my other one. So when we're making a line, usually we go for the slope-intercept form for a line, y equals order mx plus b. So the first thing we find is the slope. So what's the change? And this is our y-axis here, and this is our x-axis here. So it's always, the slope is always change in y divided by change in x. So for my slope, my change in y is going to be, I kind of wrote through that, 2181, is that right, for 1984? Minus the previous record in 1952, which is 23.7. Divided by the change in time. So that's from 1984 back to 1952. So you can either use the same points as me or pick points that fit the line you drew on your paper. And then we got to clean that up, whip out a calculator. So 21.81 minus 23.7 gives me negative 1.89 as my numerator. And my denominator is 1952, so that's what, 32 years? It's 1984? Help me out with my subtraction here.
32?
32? Yeah, so my denominator is 32. And we could clean that up further by just finding that as the decimal. Divide that difference right there by 32 years, and I get a slope of negative 0.059-ish. So I mentioned the other day when I'm making calculations about based on data, I usually go one more decimal point than the data has. The data has how many decimal points in it? 2 at most. So I would take this out to 3 places. So I'd call the slope negative 0.059. So I think my slope m is about wavy equal side negative 0.059. All right, so we've identified m. Next, we got to find b. 2 ways to do that. The easiest way is to plug in things we know. For example, we know m. We also know an x value and a y value. We could either go with this x and y or that x and y. And we can backtrack and find b. So right now, I think I'll go with the 1984 one. I have 2 points. I have 1952 with a record of 23.7. My other point, I think, is on my line is 1984. Slope is, let's see, 21.81. And we think the slope m is about negative 0.059. We're trying to fill out the equation y equals mx plus b. And we're just going to plug in, let's say, this second point in the slope, and then B will be the only thing missing. So if I plug in Y is 21.81, M is negative 0.059 times X, and we put that in parentheses, 1984. Then B is the only thing missing, and I can do a little arithmetic and solve. So first, I got to carry out this multiplication there. Google says negative 117.1818. Anyone else get that? Yeah? No?
I was doing my own.
I used a
Use
different number,
points?
but
Okay.
mine's close, yeah.
All right, so I'm going to go with mine, negative 117.18. So that's this number right here. And then I have to get this to the other side to figure out what B is. So I'm just going to add that over. And so it looks like B is 138.99, or about, I guess we can go with that, or call it 139 if we rounded. Let's figure out what all this means. 8.9. So slope, right, and Y-intercept. Now remember, slope is change in whatever your Y value is divided by change in your X values. We think the slope is negative 0.059. I'm going to put it over 1 to make it look like a fraction. What is my Y value measuring in this situation? What kind of numbers are on the Y-axis? The world record time? Okay. So this number right here is basically the change in the record. And the 1, what do the X values represent here on that graph?
Years.
Years. That's just change in years. So what this tells me, according to the line I picked, and again, every set of points will be slightly different, but this says in English, the world record will drop for women by 0.059 seconds every year. And doesn't it look like on the graph the world record's dropping a little bit every year? No. Okay, and this is on average, based on those 2 points, what we think it's dropping by each year. That's the slope. The Y-intercept, that last number, that's kind of an interesting number. The Y-intercept, that's a point, 0, whatever that number is. Okay, so remember, this 0 is X here. In this case, Y is going to be that 138.99. Okay, so 0 for X. What is X measuring again?
Years.
Not just time, but the year. So in the year 0, the world record was 138.99 seconds. When was the year 0? 2008. Okay, what year is it? 2018 years ago? Were we measuring this then? No. So Y-intercept isn't necessarily meaningful to us here because of the way we calculated it, but it's still part of drawing that line based on the 2 scales on the picture. So if we trace this, here's what, 1948, here's 2076. If we trace this all the way back to the year 0, on the y-axis, we'll hit 139 seconds for the record. Okay. That's not really all that useful. But that's what we calculated to get that particular line right there. The biggest point here is the slope. That tells us how to change from one point to any other point. All right. So let's make a prediction. I did not pick, let's see, highlighter, red, highlighter, red. I didn't pick, say, this point right here. That is in, I lost track there. 1976, I think. Yeah. So what I want to do is I want to plug 1976 into the equation and see if it comes up to a number similar to 22.37. So we're just going to check our model, see how it is acting there. Okay, so our current model, again, at least my version, yours, maybe you did a different one, that's okay. You should have numbers that are relatively similar. So I've got y equals negative 0.059 times x plus 138.99. What I'm curious about is what happens if I plug in x equals 1976. What's y going to be equal according to my model? So either whip out your calculator and plug it into my model or plug it into your model. Let's see if we get a number that seems reasonable on the graph. So, calculator, go. Negative 0.059 times 1976 plus 138.99. And my calculator says it predicts a world record of about 22.406. What did the actual data say? 6.
The actual data was 22.37.
20, and so that's in the ballpark, right? And didn't it look like that line was, that point was pretty close to the line, at least on my picture, right? So whenever you do this, in this case, I was predicting within the data set with my model. So predict within the data. That's called interpolation. When we try to project outside of the data, either out in the future or in the past, where we didn't have those numbers, that's called extrapolation, right? And so one reason you were asked here to look up some data that's not listed here is to see where we can go. So we'll do an extrapolation calculation, and then we'll look up some data on the internet and see what we find. So we were asked about what, 2008 on here in question number 14. All right. What's that?
Or, sorry, 5 minutes. Yes.
Yeah, they said find data after 1992. We'll look that up in a minute, and then compare your predictions for 2008. So we're going to use, so this isn't quite what the project was asking me to do. I'm just kind of modeling how to take a set of 2 columns and find a line based on them. We'll do another example of that in a minute. So if we let x equal 2008, that is outside of the current data. It's the current data that allowed me to make that equation. Those equations we call models. And so what we're going to do now is we're going to extrapolate with the model, which means look outside of the data. So looking outside of the data is called extrapolation. And so we're going to calculate the world record time by using that slope we calculated, multiplying it by 2008. And add in that strange Y-intercept. According to my model, in 2008, the world record will be 20.518 seconds. If you're using your model, you might have a slightly different answer than that. 20.5. Does that seem reasonable? When I look at the men's data, it says women might catch up to men, right? Because men have data in the 19s and the 20s there. All right. Anybody with a computer or smartphone? Let's see if we can find some world record times on the 200 meter. So let's see.
For women or
For women. Women's Olympic 200 times. All right. 200 meter. What's this one have? Pictures. Oh, I want actual view. Oh, here's some. Are they giving me numbers? Okay, here we go. I got some numbers. 2008. It looks like gold medal was 21.74 seconds. So is that is slightly slower than what we predicted. I predicted 20.5-ish. So here I have 2016, 2008, 2000, 1992. Oh, there's 1996. Oh yeah, this is it. Yeah, so I just searched for women's 200 meter times. All right, so let me type these up so we all have them. Let's see. Anybody have, let's see. Taylor, on your computer, do you have a Google Sheet open maybe?
well, my stupid computer doesn't work.
Okay, I'll just get 2 tabs running here. And I'll share this with you guys. Drive. Now, let's make a new sheet. So I've got year, and I've got the record time. Let's pull this over here. All right, so where did we leave off again? 1992. So this claims in 1992 it was 20.81. Is that what our table says too? Yep. Okay, so we need to pick up with 1996. And that is 22.12. And then 2000, and that is 22.27. Oh, we're getting slower. 2004, 22.05. Still not back in line with 1992. Let's see, 2008, which is the one we just tried to predict. That's 21.74. And then 2012. So this again is part of the question 14 on that activity. And 2016 says 1.78. Interesting. Okay, so what we're asked to do again in, they said to also find the men's. I'll let you guys look that one up. How did they compare in 2008? Use the data from part E, add it to the scatter plot on the previous page, use the new trend lines to predict. Okay, so what we want to do is we want to add this to that data there. So I need somebody from the audience here to read me a bunch of numbers. Who's my volunteer? Okay, so just start reading me the women's world record times back from, what did we start, 1950-ish?
On here.
Yeah, from the first page there.
On 1948.
Yep.
24.4.
Okay.
1952. Oh, you're not putting the year.
I'll put the year in after. It's,
Okay.
but I just need the numbers. 20.
23.7.
Okay. Next.
23.4.
Okay.
24.0. 23.0. 22.5. 22.40. 22.37. 22.03. 21.81. 21.34. And 21.81.
Okay. And then we have these new ones here. Just back up. Okay, so there's all the data right there. So I'm just going to throw this on a graph on a spreadsheet, and then again, I'll share this with everybody. I'll put it on the main page. So this is 200 meter records. And what's that? I'm going to add the men's to it later, but I just got the women's for now. Oh, I should make a note here. You're right. Let's insert a row. Put women right there. Okay. So I'm just going to ask the spreadsheet to graph these for me. And this is kind of cool. I don't think I demoed this last time. All right. So it's making a line chart. Is line chart appropriate here? Yeah, line charts usually for things that change over time, and that's what I have here. What I really want is a scatter plot because I'm trying to find a straight line model for this. So I'm going to change that. Chart to a scatter plot. And this is the cool part, because it looks like you guys weren't really enjoying finding that as line as much as I was. No? Okay. So the computer can find it for us. So our original data went up to 1992, which was right here. And we did have a nice downward trend, but then all of a sudden, look at it. It looks like we kind of hit a wall. We're kind of oscillating around some, like we're reaching some limits of people, maybe. So what you do on a spreadsheet, and Excel's a little bit different, is under Edit Chart, under Customize, Series are the points I have there. And what I want to do is get a trend line. And so what the computer will do, it will calculate a trend line for me. And it does it in such a way, let me get a label on there. Use equation, sure, throw that in there too. All right. It does it in such a way that it's trying to balance. So remember I said when I draw a line, I try to balance as many points above as below, kind of. So anytime, if you plug in a year like 1976, my line says the world record's up here, but the actual data says it was down here, right? So there's an error every time I use my equation, right? Once in a while, it comes pretty darn close to a point, but it often doesn't hit a point. So the vertical distance between any of these points on the line, that's the error. So here, my line does an overestimate. Over here, my line does an underestimate of the actual one. So this kind of line that the computer does here, the trend line on the computer, it tries to minimize those vertical distances. Okay? And that's called a least squares or linear regression line. Okay? And it came up with a slope here, including that extra data of 0.0336. That's not too far. I guess that extra data really did make the slope a little more shallow. And then we have a weird Y-intercept, but it's the slope that's more meaningful. Just to do it a little bit differently, let's make a copy of this. That. If we go with the original data, which went up to 1992, instead of us guessing at 2 points, if we use the mathematical technique that the computer has built into it, you got to do a scatter plot to get that option of series trend line. And then I want to see the equation. Put that in there too. It says the slope was about negative 0.06. I found negative 0.059. So that's in the ballpark of what I found. Was your slope pretty similar?
Mine was negative 0.061.
Okay, so that was pretty close. Did you do a different one or the same?
Different.
Okay, yeah, so we're all in the ballpark, right? We're all slightly tilted, but in the right, and we're all in the same direction, roughly the same slope. This is supposed to be like the best slope for these points. When we add in the extra data, we're not dropping anymore, really. We're just kind of stuck around 22 seconds. Then that skews the line to be less steep than it was before. Okay, so now they're saying that the computer says, well, a slope of this is negative 0.0336 is better. They give an extra piece of information, called r squared. They're saying r squared equals 0.068 when I include all of data from 1948 on. When I include just the data up to 19.2, they give me an r squared of 0.9. Let me explain what that means quick, and then we'll move on to another example. So we're trying to find what's called a linear model. And there's a variety of ways to do it. First, we tried the method of picking points. That looked nice, right? It wasn't really, there was no system to it. We just kind of threw a ruler down and said, this line looks nice to me, through those points. I had the computer do what's called linear regression. And if you take a couple of core classes in statistics, you work up to how linear regression works. We're not going to worry about that. It's kind of like, remember the algorithms we learned for multiplication? It's just this algorithm that picks a really good fitting line for that data. There's a number that's given called a correlation coefficient. And that's generally called R. And the correlation coefficient is going to be somewhere between 1 and -1. So the correlation coefficient could be positive, but it could also be negative. So positive just means it slopes up. Slopes up. So the line does something like that. A negative correlation coefficient just means it slopes down. If you square the correlation coefficient, it gets rid of the sign. And so a lot of times computer programs, instead of giving you R, they give you R squared. Right? So we have a relative of the correlation coefficient called R squared. And it's going to live between 1 and 0. And basically it says how good of a fit is this line to the data. So our first group of data where we only went up to 1992, we get a correlation coefficient of 0.9. And what that means is the line is a pretty good fit to the data. So there's always going to be natural variation in a population, but wouldn't you say that data kind of lines up in a downhill trend? It doesn't really look curved, does it? And it doesn't look like a cloud of points, like a swarm of flies. Right? It looks like it has a downhill trend to it. Right? And that's what the correlation coefficient tells us. If the correlation coefficient is close to 0, it means you just have a cloud of points and this is bullshit. Right? So if my data looked more like this, and I tried to draw a line through it, you'd be like, why did you draw a line through that data? It's a cloud of points. Right? So in a situation like this, I would expect R squared, oops, I'm supposed to say R squared, do that again. I would expect it to be around 0.005, something super low, meaning this was a pointless act. So usually if R squared is bigger than, say, 0.5, there might be some meaning in the line that you found. If the line's less than, if R squared is less than 0.5, so here I have 0.005, right? That's just, it's garbage. It's not really helpful. Sometimes you might have data that does something like that? Do those points line up? No, but is there a pattern though? Yeah, they have a curve to them. That's a whole different thing. And there are techniques for trying to calculate what curve might best slide through those points. It's related to linear regression, but it's slightly different. Okay? And on a computer, they usually will offer you options. So for example, with this data, let's see, is this the second group or the first group? That's the first group, yeah. This one kind of starts to curve. It starts to get a hockey shape kind of thing to it. So when I edit, I have the option under customize series. Instead of finding a linear regression, I could go for exponential or polynomial or logarithmic or something else. So I might have reason to believe it's exponential. And so I could go try to find the exponential model to it. And so it'll give me a slightly different equation. It'll describe the equation and it'll show the graph right here. Doesn't look too different, does it? Yeah, it has a slight bend to it, but it's hardly noticeable. Is this a lot of data? No, it's not a lot of data. But sometimes you can do pretty good predictions with a small data set. It just kind of depends. Okay. So I'm going to leave you guys to play with that one some more. Let's do another example of linear regression, then we're going to move on to the normal distribution. So I'm going to bring up a data set from a different class. Which one do I want to use? No, that'll work right there. Numbered. Oh, actually, we'll try that one. Chapter 2. Lines. Ooh, that's a good one. Yeah, let's do this one right here. All right, minimum wage data. So we're going to do this one a little bit different. Remember when we found the Y-intercept for that one we just did about the world record? Y-intercept means when X is 0, and that put us way back when we changed from AD to BC, which seems kind of ridiculous. Why would we go that far back? So often what we do, instead of using the actual year to plug in for X, we pick a starting point and let that be year 0. And then we measure everything else in years after that. Okay. So on a piece of paper, if you like a piece of graph paper, I have some here. Grab one and pass it around. What I'd like you to do is make a plot of these years and those minimum wages. And we're going to attempt to find the line again.
No, you're fine.
All right, so here's our data. Usually when I make a graph, I try to put some kind of label for each axis. I decided to go 2, 4, 6, 8, 10. On yours, you can just go 1, 2, 3, 4, 5, 6, 7, 8. It'll be good enough. All right, so then let's get some points. And so do your best to plot each of those points. I think they look something like that. If you try to draw a line between the first and the last point, does that look all right? Not too bad. Yeah, so let's say that's going to be our model, the first and the last point. And I'll ask the computer to do it too and see what it says. So the twist in this case, instead of calling this 1990 and 95 and 2000, we're essentially going to relabel that axis, and we're going to call it 0, oops, marker, 0, 5, 10, 15, and 20. So our x values are going to be how many years after 1990 are we looking at, right? And we'll use this to make a prediction. So these are my x values in this column right here, and these are my y values. So we're going to use these 2 points to try and find the line. So first thing, come up with a slope for this situation. You get the slope of 0.2. Everybody else get that? $1990 to 2010, it went up $4, and it took 20 years for that to happen. So 4 divided by 20. One of the most important things about when we find this kind of straight line model is, what does the slope mean? So remember, slope is change in vertical change divided by horizontal change, right? What's our y-axis measured in?
Dollars.
Dollars. Okay, so this number is a dollar measurement. And what's the denominator measured in, the x-axis?
Years.
Yeah, so what we've calculated is that minimum wage based on this data seems to be changing by about 20 cents per year. How about a y-intercept? Is that going to be easy to find here or hard like the previous problem? That's okay. Yeah, most of you probably haven't done lines in a while. So remember, we're trying to find an equation for this blue line. It's going to look something like this: y equals m times x plus b. And that b is what we call the y-intercept. And the y-intercept is the place you hit the y-axis at. Yeah, we got it. Yeah, 3.25. That's another thing. It's way more convenient to say, hey, let's let this just be years after whatever. So if we let, for example, with the world record times, if we chose to say, let's let this be years after 1900, it would have been way easier to do, or even better, 1948, because then 1948's time got to be our y-intercept. Okay, so that's usually what people do in situations like this. Yeah, so we think our model for the minimum wage is y equals 0.2 times x plus 3.25. And just a reminder, x is the years after 1990. And y is the minimum wage in dollars. So let's predict what's the minimum wage going to be in 2020. over the last few years, there's been lots of states playing around with minimum wage, and it's been a national dialogue too. So if I want to look at the year 2020, I have to backtrack and say, okay, how many years after 1990 is that? It's going to be 30 years. So that means we want to plug in x equals 30 into our model. So we then calculate y is 0.2 times 30 plus 3.25. That come out to around $9-ish.
9.25.
$9.25. So we're predicting that in 2000, according to the limited data we have, the minimum wage will be $9.25 in a couple of years.
Let's hope not.
What's that?
So let's hope not.
Yeah, that's pretty low.
What is it in Oregon?
Right now it's 10.
$10 in Oregon. So with the calculation we just did we just interpolate with the data or extrapolate the data?
Extrapolate.
Yeah, that was an extrapolation extra. It was outside of the data. Yeah, so this is an extrapolation. What's that?
That's better.
Yeah, so we extrapolated. Based on our limited data and the trend line we found, we think it's going to be $9.25. If I plug this data into Excel or into Google Sheets, it'll give me a slightly different slope in Y-intercept, but they'll probably be pretty darn close. Okay. All right, so straight lines. Next.
If we didn't have our Y-intercept.
If it wasn't on the table?
Then we would just have to plug 2 points into the equation and
Yeah.
solve for B, right?
Yeah. Yeah, so let's actually do that just for fun. And you know, the easier way to do this and the way I recommend, I'm not going to test you guys on lines. You can just, what would be, you decide what would be easier, to type these numbers into a spreadsheet and say make a scatter plot and tell the scatter plot to make a trend line, or you could do these calculations, whichever is least painful, you decide. Okay. But let's double check our Y-intercept, but using the other point. I lost my magic pen. There it is. And you get a run soon?
5 minutes.
Okay. Yeah, so as soon as we do this, I'm going to move on to some stuff in section 4 I didn't get to last time,
Okay.
based on standard deviation called normal distributions, and I'll record that in a second video.
Do you have the take-home test for me?
Yes, I think I am ready to give it out. So you can have my draft copy.
Okay.
I probably won't change it. The data for number 1 is on the website.
Okay.
Right near the top. And you have until next week to turn it in. You'll be back Wednesday, right?
Unless something happens.
So, for example, in the problem we were just working on, we know the slope is 0.2, and we had a point that, what was it, 20 years later? 20 years later, the minimum wage was $7.25. So, if X was 20, Y was 7.25. So we can use that point and the slope by plugging into this equation, Y equals mx plus b. And then, because this is my y, this is my x, there's my m, I have everything but b, I can just plug in and solve. So let's do that and see what happens. So the 725 goes for y. M is 0.2. X is 20. So we've got to clean up. What is 0.2 times 20? 4, yeah. And you know, sometimes the arithmetic's a little bit messy. This time it's not too bad. Next step should be to do what? Subtract 4. And we got the same number we found earlier of 325 for the Y-intercept. So once I have that, I can state my complete model. I can say, oh, it's 0.2 times x plus 325.
Isn't that what we just did?
With the world record times.
The first one seemed way more confusing.
A couple of reasons, I think. One, the numbers were messier, and 2, your mind wasn't turned on to this stuff yet.
Yeah.
Yeah. So this is, the second example. It feels a little bit better. When was the last time you graphed lines and found slopes and percentages? Yeah, right. So it's we're dusting off some some older information. And for, again, the kind of work we're doing, it's okay, it's good, great if you can do this, but we have a wonderful spreadsheet given the data that can do it for us. 10 minutes. Does anybody want to see that again? I think you got it. I think it's relatively
You just
straightforward.
put in.
Just say, give me a scatter plot,
Informations and hit graph,
hit graph, scatter plot, and then choose the series trend line option.
And we'll need to know how to put equation.
Oh yeah, then there's an option to show the, yeah, because otherwise it'll show the line, but it won't tell you what the equation is, which kind of, okay.
And will we have to explain our.
You will not. No, but I thought I should tell you that. It's an important part of linear regression, yeah. But that's not something I'm going to test you on, but it's just whenever scatter plots are made, if things look like they line up, it's very common to make a linear model and use that for predictions. Okay, so more playing with data. So we talked last time about an idea called standard deviation. So I just want to review what standard deviation means. And I'm going to use that data we just worked on. Mean and standard deviation. So the data we were just playing with had, I want to start over. Let's see, what time is it? 4 o'clock. I can always break the video after. Yeah, let's go with it. We had X's and Y's. Our X's were 0, 5, 10, 15, and 20. And our Y's were 3.25, 4.25, 5, 5, and 7.25. And for this one, since the years are changing regularly, I just want to focus for now on the minimum wages. So the first thing I'd like you to do is find for me what is the average minimum wage in these years. So to add things up right. That was bad. 4.95?
Yeah.
Okay. So the mean often isn't actually a number in the data set. It just works out that way. I mentioned an idea the other day called deviation. And deviation is just distance from the mean. And we find deviation by taking a particular number and subtracting the mean from it. So if I do 3.25 minus 4.95, what do we get? 1.7, but negative? Is that right?
You take any number,
What's that?
any number.
Any particular number. Just pick a number, subtract the mean. So for example, in this first line here, I'm getting, shift this up a little. I'm getting a deviation of negative 1.7. Because it's below average, it's a negative number. 4.25 is a little below average too, right? So what's that? Negative 0.7. 5 is a little above average. It's plus 0.05. And then 7 is above average. So let's see, what's that one? 2 point something. 0.3. So those numbers are right there, what we call the deviations, how far each number is from average. So anytime we have data on an individual, on some event, things are above average, things are below average. It's just the way it goes. The deviation helps us talk about the spread of the data. And how far from the middle? Here we're saying the mean is the middle. How far from the middle is the data? And it's often helpful to get an average spread. Standard deviation is one way of many to measure average spread, right? It happens to be like the most popular method. So just a note on that. Standard deviation is a measure the average spread of the data. Some data is more tightly packed, other data is more spread out. Standard deviation helps us figure that out. The calculation of standard deviation is a pain in the butt. I demoed it in the last class. First, you have to find the deviations. There were two kind of versions we looked at the other day. One was called the mean absolute deviation. That's never used in reality. It just appears in some textbooks. Standard deviation says you have to square those deviations to get rid of the signs. Then you have to add them up. Then you average them by dividing by how many there were. That's the n. And then you take the square root of that to kind of undo squaring them. That's the calculation of standard deviation. Would you ever have to do this by hand? No. We do it on a computer these days. So even when I teach statistics, I don't make those students do it by hand either. Okay? Because we have technology, we push a button and it happens. But the idea is things aren't average. To measure how far something is off from average, we calculate deviation. How do you calculate deviation?
You subtract the number.
Yeah, just subtract the mean from the number. Yeah. So this right here is deviation. So this is just one way to figure out how to average deviation. And for some weird mathematical reasons, this is the best way that we know of. Okay. Even though that bad idea that's in the book I talked about last week, called the mean absolute deviation, that seems easier, but it has problems that I can't explain right now. So that's one version of standard deviation.
That E symbol stands for.
Oh, I'm sorry.
Yeah,
so sorry, I don't know if I've talked about that before. Did I talk about this symbol before with you guys? Okay. This is the Greek sigma. Oops, that's not a pen. Again, this thing right here is the capital Greek sigma. It means sum. Sorry about that. Like you ever notice in Excel, and in Google Sheets, there's a button that looks like that, and sometimes it's called the auto sum button.
I'll just.
Yeah, thank you.
That would be all of them.
So this means add up all those guys. So like the other day in class, oops, wrong way. I made an extra column here where I squared them. So I had, whatever this is, oops, squared, and this guy squared, and so on. I square each of these things.
And that's just,
And then I added them up. That's how you find standard deviation. Yeah, you square them. First you calculate it, then you square them, then you add them up. You divide by n, because that's average, right? Divide by how many. But then we have to do the square root to get it back to the regular data, to give it some meaning. Yeah.
And before you square root it is the variance?
Yes, that's right. It's the
I was
variance
thinking-
before you square root it, yeah. So, and that's used in some areas of statistics. You will probably never come across it in the schoolwork that you're going to end up doing, but let's see. So before I take the square root, that part right there is referred to as the variance of the data. After the square root is called the standard deviation. And what's more meaningful for us is that in a spreadsheet, there's a button we hit and it calculates the standard deviation for us. So I'm just going to take a data set and I'm just going to demo a couple of things and I'll kind of try to explain the meaning of it as we go. So let's see. On the home page, I added a new option at the bottom of information called Some Oregon High School Data. Some Oregon High School Data. There we go. The first data set about writing standards, you're going to analyze that data set for your take-home exam. And I'll give you that exam today and you've got a week to play with it. So I'm going to do some similar things with the math data. And you'll get a view-only link because I own the data, you don't. So you'll have to make a copy right away. So I'm just going to remind you how to do that. You just go to File. Yours won't show any of the toolbar items here. It'll just say in blue, view only. And so you just go to File, make a copy. Does anyone here prefer to work in Excel instead, or are you guys okay playing with Google Sheets? I highly recommend getting used to Google because almost every school district has a Google account now, and teachers use it, and the students end up using it. Let's see, make a copy. And I'm going to call it Gary's version of, and my Math 13 folder. Okay, so in the take-home test, I'm going to ask you to analyze the 2010-11 data, the percentage of students in a given school that met or exceeded the standard. Right? This one is about the math standards. The one you're going to analyze about the writing standards. So I've got all this information here. For some reason, we don't have information from the Adele School District. The Adrian School District, 50% of the students met or exceeded. And notice there's a lot of variation here. 71, 86, 73. So what are some things I'd want to calculate about this right here based on what we did in class before? Yeah, I'd want to know the mean. What else? The min, the max. Yeah, definitely. What's the lowest school? What's the highest school in terms of percent of students that exceeded or met the standard? The median would be another one I'd want to know. The range might be a good thing to know. Yeah, how distant is the lowest school from the highest school? Notice I'm going to have to scrub the data a little bit because there's some weird stuff in there. So here in Monument, it said it was greater than 95%. Why did they do that? I don't know. I got this off the Oregon Department of Education website. So, you know, just scanning it, I see, okay, I got a little data scrubbing to do. Because what's the computer going to do when it sees that symbol? It's not going to treat it as a number when I try to do the average, for example.
You just delete the symbol.
Yeah, so I would just go in and delete the symbol, or I would delete the school. So I have to make that choice. So you might want to make a little note to me, hey, when I scrubbed the data, I decided to delete those weird symbols, or you could just say, I didn't know what they meant by greater than 95%. Like, what does that mean? 96%, 99%? So I just deleted it because I thought it was confusing data. So you'll have to make that judgment call. So there's only a couple of them.
Same thing for the ones that don't have data, just.
Yeah, the star, it will just ignore. So it turns out there's two versions of most statistical functions. One of them ignores anything that looks like text, and the other version treats anything that looks like text as a 0, which can be dangerous, but sometimes it can be good. And there's a reason for that that's kind of weird, but so for
blank, does it treat it like a 0, or does it treat it?
If it blank, it treats it like a blank. Yeah, so blank is in most formulas different from a 0. Not all the time, but for statistics in spreadsheets, a blank is not a 0. Yeah. So if at the bottom I wanted to calculate the average here, so I'm going to put a little note that I'm doing the mean. I do equals, I start typing it. If you're not sure what to type, I don't know if I went over this before, there's this button right here, allows you to look up more functions. That takes you to the Google search page where you can search for different kinds of functions. So basically, I start typing whatever I'm looking for, hit enter, and it will tell me anything related to the word standard. And I can look through there, and I'm trying to find, so I'm getting a lot of stuff. Ooh. Statistical STDEV calculates the standard deviation based on a sample. What was the other kind of thing we deal with in statistics? Samples versus, starts with a P, O, P, populations. Yeah, samples versus populations. And it turns out a lot of statistical formulas treat samples different than populations. The calculation can be slightly different sometimes. We don't need to worry about that because we're not hardcore statisticians. But usually what I do is I start looking here if I'm not sure what function I need. And usually their descriptions are like not very good. And so then I go search the internet for Google Sheets, this formula, and somebody will write up a better description somewhere. Even Excel is notorious for their descriptions were written by engineers. Engineers are, they're kind of human, but they don't have the same communication skills necessarily. I love all my engineering friends out there. Just, you know what I mean.
And your video game friends.
And my video game friends, yeah.
We really got a variety.
So notice there's an average and there's an average A, right? So what's the difference between them? The average ignores text, just makes believe it's not there. And the average A, it doesn't show it there, but it actually treats text as zeros. Okay? So sometimes you might have a reason to do that. Usually I don't. So if there's an A at the end of the statistical function, usually I don't use those unless somebody gave me a good reason to use it. Okay? So I want just the regular average. And then I highlight the data. Can I just hit the column heading in this case? No.
No.
Why?
Oh, because it's labeled at the top?
No, because I'm in the same column.
Oh.
Because then it would get confused because it would try to throw the average into the average, and it would probably give me an explode, I'm going to explode error. Yeah, so in this case, since I have it in the same column, I have to just highlight the numbers. Since the data is not scrubbed yet, it's going to treat those numbers with greater thans as not there. It's just going to ignore them. And even if I highlight the title accidentally, it's just going to ignore it in this particular function. So ignoring the asterisks and those greater than 95%, it says the average percent of students who exceeded or met the standard was 64.94%. If I throw in those greater than 0.95s, it's going to raise it up just a little bit. Okay. Next thing I'm going to do is the standard deviation. That's usually abbreviated STDEV. Equals, if I just start typing ST, it brings up a whole bunch. And the one I recommended is just the one called STDEV. Okay. Generally, what we're working with is samples, not whole populations. And there's a minor difference between the other versions. So same as the average, I just highlight the data. Since it's in the same column, I can't just hit the column heading. Okay, so I get a standard deviation of about 12%. Okay, so we're going to take a look at what that means right now. So let's highlight those numbers, bring it into a new screen. So here is what we're going to do together. Oops. Oh, didn't do that very well, did I? Escape, TV. Again. Okay, we are going to make a number line. In the middle of the number line, we're going to put the 64.94. So let's draw ourselves a number line. And right in the middle of our number line, we're going to say, hey, that is 64.94. And remember, mean is a measure of center. What's our other big measure of center? The what? The median, correct, yeah. And that is a percent rank version with a slightly different idea. So then what we're going to do is in the remaining distance I have, I'm going to make 1, 2, 3 marks. So right in the middle is my mean. I've got 3 marks to the right. I'm going to do the same thing to the left, try to keep them equally spaced. 1, 2, 3 marks to the left. So to the right here, what I'm going to do is I'm going to take the mean and I'm going to add to it 1 standard deviation. I'm going to call it an S. And then I'm going to add another standard deviation to get to that point. And then I'm going to add a 3rd standard deviation to get to this point. So plus 3S. So let's round these numbers a little bit to make it easier. Let's say the mean's about 65. And let's call the standard deviation, it's pretty darn close to 13, right? Let's just call it 13. So let's see, I think I'm going to just cross that out and say, hey, 65 is close enough. All right, what's 65 plus 13? 78. Then I'm going to add another standard deviation to that. So 78 plus 13 would be 91. And add another standard deviation to that, and we get 104. Now, remember, these are percent of students. You can't have 104% of students do something. There's only 100% of students to deal with. So this is beyond reality at this point. Sometimes that happens, sometimes it doesn't. We want to go the other direction now, too. We want to take the standard deviation away from the mean. So subtracting 13 once, I get 52. So that's minus 1 standard deviation to the left. I'm going to go 2 standard deviations to the left, so subtract 13 again, and I get what? 39. And subtracting 1 more time, we get 26. And there's kind of this common rule of thumb. So a common rule that within 1 standard deviation of the data, so within 1 standard deviation, we expect to have around 68% of the data lives in there. So what this tells me is if I look back at that spreadsheet, 68% of the schools should have a ranking somewhere between 52 and 78. We'll check that out in just a minute. Okay. Within 2 standard deviations of the mean, so 2 standard deviations below is 39, 2 standard deviations above is 91. So if somebody has a score between 39 and 91, that means they are within 1 standard deviation. Oops, I should have said within up here. Within 2 standard deviations. They're supposed to be about 95% of the data. And then within 3 standard deviations, for a lot of data, so this is within 3 standard deviations, we should have about 99, almost all of the data should be within 3 standard deviations. So I'm going to sort the data and check it out and see what happens there. Question?
I'm just confused. How we can have 99% and 95%.
We'll make a histogram and I'll show you. I think the histogram will help a little bit. Okay. So I'm just going to check out a couple of things on the data. Back to my spreadsheet. Where are you? Right there. All right. So I'm going to highlight all of the data here. Oops, there's more data to the right. Darn it. I'm going to zoom out for a sec. Just up to F there. Okay. So I'm going to choose, I talked about this before, data. I like to use the sort range option and indicate my data does have a header. And I want to sort by, in 2010-11, the percent of students who met or exceeded the outcome, go from smallest to largest. All right. And so the 99, so these are in the largest category. I forgot to scrub that data. And these are essentially non-existent. I can't call them zeros, we just don't have that data. So they didn't report at that time or they didn't report it at all. So we've got a high of 95-ish. We've got a low of 20. Okay. What was our third deviation? 26? Third deviation below? Yeah. So in this particular data set, we'll get back here. Starting at about right here. Ooh, skip some data. What did I do there? Look at that later. All but 2 of the schools were above 26. And what was our max? 104. Everybody's below that, right? So let's get a count. How many data items do I have here? Down here. And I'm going to make it a percentage, which is inappropriate. Whoa, what happened? Accidentally deleted. Format, number, claim number. So I have 173. All but 2 of them were within that range, right? So just a note on within 3 STDs, I have 171 out of 173 schools, which is 98.8% of the schools, which is pretty close to what that rule of thumb I gave you said. If we check some of the other boundaries, like the 68% one, so how many schools had 52 or higher and 78 or lower? So I just want to look at that group of schools. So right here, I'm going to count in 2 STDs. So what were those numbers again? I forgot now.
Within 1 is.
Within 1 is what I want to do, not within 2. 52 to 78. Okay, type that on. Fix that. So, okay, so here's 78.3. I'm going to say that's too high, so I'll start with this one and go back till I get to 52-ish. Okay, so here's 52 exactly. So close parentheses, hit enter. This is within 1 standard deviation. So there are 124 of the schools out of 173. So 124 out of 173, that's about 71%. What does my rule of thumb say? 61% of the schools, are we in the ballpark? Yeah, 71's kind of close to 68. So does every data set fit this pattern? The answer is no, but a lot of data sets do. So what we're looking at right now is what's called a normal distribution. So a normal distribution is what they call a bell curve. And I'll grab this one right here. Let's see, tab. Oh, that's not what I want. I just want to see the image, please. An image in new tab. There we go. So here, notice this funky symbol. I think I brought it up in the last class, maybe. Does that look familiar? No, maybe it wasn't this class. What's that? It's a Greek letter. It's called mu. And it's what's commonly used to talk about the mean. So mu is the symbol in a lot of statistics books they use to represent the mean. This is the lowercase Greek sigma. Guess what it stands for? There's a minus sigma there and a plus sigma there. Yeah, it stands for standard deviation. So what this saying is find your middle, go 1 standard deviation to the right, go 1 standard deviation to the left, you should find that if your data is normally distributed, about 68% of the data is within those two numbers, whatever they are. So that's what I was testing out here with this data. Okay. So did I have about 68? I had 71. Did I have 99.7 within 3 standard deviations? I had 98.8. Okay, so here I was a little high, here I'm a little low. We can check the middle number to see what that looks like with this data set. So for our middle number, that would be between 39 and 91. So that's wrong one, this one. So within 2 STDs, so 91, so about here, sorry, I forgot the other number already. Somebody help me. 39?
Yes.
All right, so I guess that 42 is the next number above 39. My spreadsheet says there was 166. So if I take 166 divided by the total of 173 schools, I have about 95%. So let's format these as percentages. And sorry, I did them out of order. Let's move you underneath. So we've got within 1 standard deviation, 71%. Within 2 standard deviations, we have 96%. Within 3 standard deviations, 98.8. Normal distributions are supposed to have 68, 95, and 99.7. Okay. So then you would argue, are we close to these or are we far off from those? Yeah, we're close. This one's not too bad. This one's pretty darn good. I'm a little low there. I'm close. The next thing we look at to see if, now not every data set is normally distributed. I'll talk more about the distribution in just a minute. The next question is our data have a symmetric looking histogram? A histogram is a distribution. Remember we call it a frequency distribution table, and a frequency distribution histogram are the proper names for it. So I can just go to my computer here and say, let's just grab, let's see, ignore those. I'm just going to grab this group right here. Remember, it makes a quick histogram without having to make a table. So insert chart. That's not a histogram. That's just a bar chart or column chart. I want a, got it right there, histogram. Okay, so here's the histogram. I'll zoom out just a touch. Does that look roughly bell-shaped? Yeah. Is it symmetric? Like, is it spread out evenly like this picture is right here? So it's a little bit skewed. Remember, does anybody remember, is the skew toward the hump or the tail from last week? Yes, it's toward the tail. Yeah, so this data right here, I would say the tail's to the left. So we would say the data is skewed left here. Okay, because we have some stragglers out there. Is this the best histogram I could make? I have no idea till I make like 5, and then I can say, okay, this one's best. So usually I go to customize next, and under histogram, I play with the bucket size. So instead of auto, this is giving me what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 buckets. Oh wait, no, the bucket size is the width, isn't it, here in this program? Can't remember. Ooh, that's 1 bucket apparently. What if I got 25 buckets? Uh-oh, what happened? I totally messed it up. Auto? All right. Oh, it must be, okay. So what's the width here? 0.06, okay. So if I go 0.06, ooh, I broke it. All right, let's undo that, and that happened. Okay, let's try again. 0.06 should give me roughly the same graph, almost. But if I made it smaller, 0.05. Okay, so the bucket size is the width of the column. 0.1. Bunch of different ones. That one's not bad, huh? Does anybody remember the rule of thumb for like how many columns you should have? I talked about a week ago. More than 5 and less than 20. Yeah, that's okay. Yeah, 13 is a great number, right? So I think that's what we had earlier when Google did the auto version. I think there were 13 categories. So you just got to kind of play around. So is this kind of sort of bell shape? Yeah, there are some low performing schools. If I took those out, man, that looks pretty normal right there. So people talk about normalized data. They talk about normal distributions. Not every data set is normal, or is it supposed to be? But there's a lot of data out there that is. And it's believed that most measurements related to human being type things and a lot of animals, the scores tend to be normally distributed. So if we took the heights of tons and tons of people and we looked at a histogram of heights, we would see roughly a bell-shaped curve. If we looked at a whole bunch of people's body temperatures, we would see roughly a bell-shaped curve. What number would we expect to see right in the middle of body temperatures? What do we think average body temperature is? 98.6. Yeah. Okay. So when I'm trying to determine if a data set is normal or not, there's a few things. I want to have a sufficiently large set of data. What does that mean? It depends on the data. Is this a reasonably large set? I have 173 schools. That's not bad. Do the percentages fit this rule of thumb right here? They're not too bad. And then the next question we ask is, if you make some histograms of the data, do the histograms look bell-shaped and relatively evenly distributed about the center? And here I'm like, well, I got a slight skew to the left, so maybe it's normal, maybe it's not. It's kind of close. Okay. But normal distributions are very popular. You'll see them in a lot of research and papers that you guys might have to look at in the future. You might see them. So I feel I need to talk about them. And we are almost out of time here. Let's see if there's something else. Let's look at one more quick example. Human body temperature. So we believe that for body temperature, the mean is approximately 98.6 degrees Fahrenheit. Standard deviation from the research I've done, it's about 0.7. Is that what I looked up? Yeah, it's about 7/10 of a degree Fahrenheit. So those of you with calculators out, help me out here. We're gonna draw out the idea of deviation from the mean. Now, some people are just naturally cooler than other people, and some people are naturally warmer. Okay, whether they're sick or healthy. But right in the middle of all people is this 98.6 number. So then if I measure over one standard deviation to the right, what would that be? 99.3? And if you go 2 standard deviations to the right, so 2 hops by 0.7, that would be 100. And if we do a 3rd hop to the right, we're at 100.7. Okay, and remember, this is my middle here. Going the other way, 1 standard deviation to the left, that's going to be what, 97.9? Is that right? 2 standard deviations to the left, so 2 hops, 97.2. And 3 standard deviations would be
96.
Thank you, 96.5. So if human body temperatures are normally distributed, and they kind of are, most people would be in this category over here. So somewhere in this region right here. And then as we move out, if I draw like a blocky histogram, it's going to look kind of like this. And there's a little tiny number of people that might be off even farther than that as possible. And this is that idea of a bell-shaped, oops, I'm gonna switch colors, red, a bell-shaped curve that swoops down and kind of disappears there, and swoops down and kind of disappears over there. Okay. So this is called a bell curve. A bell curve comes from a normal distribution. And distribution just means how are things spread out. That's all distribution. How are they distributed? Normal distribution. Distribution. So we would expect that 68% of people that we meet have a body temperature somewhere normally between 97.9 and 99.3. Okay. I tend to be on the cool side. My body temperature is usually somewhere over here, around 97, 98. Okay. Most people, if I go 3 standard deviations on either side, 99.7% of people, sometimes we just call it 99, we round down, should be somewhere between 96.5 degrees and 100.7 degrees. So for some people, it's normal to have a temperature of 100 degrees. Now, do you ever stay home sick from school and your parent takes your temperature and says, you know, you're not sick enough? What's a cutoff point people usually use? 100, 101. Yeah, because you're outside of normal. We expect normally people fall in here. Okay, so this would be outside of normal out here. Then there's something wrong. Something's not right. Could be a very rare individual, but most likely it's illness that leads the body temperature to be some above normal or even below normal. Right, that's possible too. Chills instead of a fever there. Just more on distributions real quick, and then I'll set you free and we'll do some more of this next class. There are many types of distributions. So some kind of measurement. Instead of having a bell-shaped, some distributions are just relatively flat. You know, maybe there's a little deviation in the histogram. Some stacks are a little tall, some stacks are a little short, but mostly the stacks are around some common height. Oops, they should have been the same size. So if our histogram looks like this, does this look like a bell shape? No. These are mostly the same height, right? So this would be called a uniform distribution. Uniform. And it turns out there's a lot of other shapes that kind of look like bells that aren't normal because they don't meet the percentages. There's many ways data can be distributed. Normal distributions are very popular in math, in social science, and regular science. But not every group of numbers that we collect is normally distributed. But there are some fancy reasons that we like to use them. So like when people talk about, teachers talk about grading on a curve, usually they're talking about a normal distribution so that maybe 68% of the students should have about a C. And the B's and the A's are going to be these groups up here. Down here, I have my D's and F's. Okay. Very few people get an A. Some people get a B. Lots of people get a C. Very few people get a D. Very few people get an F. Okay. So, yeah. So it used to be more popular. It's grown out of fashion, but for a long time ago, especially in university, it was pretty popular that the schools, the teachers believed that grades should be normally distributed. So even if you got a score that was over here, they redid the grade so that only a certain percentage of students get C's, only a certain percentage of students get B's, and only a certain percentage get A's.
Not ever drop someone's grade?
Yes. Yeah. If you're not in the right spot, they make those cutoff points and they now have a C, even if you got an 80%, just because of the way things fell. Yeah. So if you look at standardized tests, the scores do tend to be pretty bell-shaped around some average. That happens a lot. But it's not always the case. So they're popular, they're useful, but we always have to approach them with caution. But I just wanted you to know a little bit about them. So I'll show a little bit more about them next class. We'll tie a few things up next class. Kristen had some questions about weighted average from the homework that I didn't go over. I need to go over that. And then there's another section I haven't assigned homework yet on, and I probably won't. I'm just going to do an activity with you on it about abuses of statistics. And then we'll be done. So.
Can you help me answer a homework question about normal distribution?
Yeah. Give me 1 second. I am going to post, for those people that aren't here, on our website, the take-home test. And then for those that you are here, I'm going to print it out right now, and then I can answer your question. So let's see. Exam 1. And the question 2 here, we're going to go over how to do this one tomorrow, Wednesday in class. That's about misuses of statistics. But you pretty much have everything you need to do question 1 right now. All right, so let's print 3 copies for now. And then for people that aren't here, I'm going to post this.
No, you're fine.
Most of us are just like from everyone.
That's okay. Fine. I'll just throw everything back. It's gonna say it's great, and just throw it away, and I'm like, oh, that was not. I'm not 100% sure yet. I'll let you, I'll text you. Okay. I'm gonna go home and eat and come back and go. Yeah.
That's a good idea, keywording class.
Yeah. There is a lot of work into it.
Yeah.
At least I have a
Okay,
decent-
so Nicole, you should be able to, if you refresh your home page, you should see the link to the exam, and above that's the link to the data.
Okay.
All right, so let's see, Emily has a question about normal distribution.
Yeah, it says assume normal distribution and that the average work will is at a certain.
It's like when I'm on the phone trying to tell you. So very
Less than
What?
So
So
for
then
All right, so let me get my board here. So we got a mean, yeah, so you did the right thing. We graph out. The mean is 10, is that right?
Yeah.
And standard deviation is
Oh,
1.
sorry, no, the mean is 11.
11
And the standard deviation is 1.
is 1. So then 12, 13, 14. So that's our middle. And then the other way, 10, 9, and 8. And we want to know what percentage is less than 10. Okay. So we want to know what's in that group over there. So if we draw in our bell shape here, so that's 1 standard deviation below, right? So we know that, red here, or I guess it was blue, that in this part of the curve right here, 68% of the data lives if it's normally distributed. Okay, there's at most 100% of the data, right? So if there's 68% in the middle, what percent has to live in the tails? So if I take 100% and minus 68%, that's going to give me 32%. And yeah, so the tails have to split this. So half of that would be 16 in this side, and 16 has to be in that side. And that happens to be the left tail is what we want. So we could say 16% of the calls should be less than 10 minutes. So just kind of troubleshooting based on that normal distribution picture with percentages. Yeah, and we'll do a couple more problems like that in class on Wednesday.
And the homework for 10 courses.
Today or
What's
Wednesday.
today?
Today is the 16th.
Yeah, today.
It's due today. Okay, I will change that right now.
I didn't even see anything on the calendar. Because I was like, oh, you must have not updated the dates yet.
Really?
It's really confusing, and I know you can't do anything about it, but the assignments are in
Oh,
the section, and so on the regular like login, campus page. Or when something's up.
They should show on the calendar. Well, they show on my calendar. They don't show on yours?
I thought they did.
Okay.
I haven't looked into that. I guess
Okay.
I was looking at like today.
Yeah, I'll fix this right now. 213.